Morning, morning, morning. It's January 18th, January 19th, Friday, January 19th. Funny how time slips away. Anyway, let me say special shout out to all my Facebook people, to all my friends, those who have had great impacts on my life, one way or the other. You know, some of course have negative impacts or create negative environments, but yet I'm able to turn these things sometimes into positive. Let me say a big shout out to my friend over there in Florida, Milton Barrett, one person who I continuously speak to on a daily basis, because you feel so energized when you talk to those people who have your interest at heart. Of course, it's mutual. I want to say a big shout out to my friend in Jamaica, Roy Clark. We go way back. When I say way back, we have been trying to walk along this engineering route for quite some time. And just to pull back on Milton Barrett, if you're in the South Florida area, I would say preferably the Hollywood area, and you need any kind of service for your vehicle, from towing to a place to park, I think Milton is a person for you to call. You can be reached at 954-588-4343. That's Links. So my respect to you, my friend Links. Keep it going, man. Positive actions would only return things that are positive. And back to Roy Clark, affectionately called Nev. He has been my friend for years, someone who has impacted my life as an engineer since the start of things. We've gone to high school together, and before understanding the true meaning of being engineers, we had several great conversations on being engineers. Of course, we wanted to be electrical engineers. Now that that came into fruition, I can more or less speak on who is an engineer. My reason for choosing this topic is the knowledge or the understanding that over the years, the word engineer, or the profession engineer, or the name engineer, has been thrown around very loosely. There are many who are called engineers, but yet there's no background that speaks to engineering concepts. But who is to be blamed for that? I'm sure these people, some may know, but there are big corporations who assign these names to people who have not had any kind of formal training in such discipline. Being an engineer who has gone through all the training, from undergrad to graduate level training, I am privileged to speak on this subject. Who is an engineer? Well, let's say what's engineering. Engineering is the application of science and mathematics through, what must I say now? I want to give a very good definition that's not so not so complex. So application of science and mathematics through the properties of matter and sources of energy for the good of mankind. So what does that mean? The engineers look at all physical properties, physical entities, apply math to these physical entities, and come up with some utility for man, or some use for man. So what am I saying here? You know, I've kind of stumbled over that a bit, but you know, I hope by the time I get through with this drive time, most things may come clear. I'm speaking mostly to the youths who are thinking of assuming or taking on this task of becoming engineers. What is fundamentally true, or the fundamental and foundation of engineering, is math. Math and sciences, physical sciences. So you're talking about math, physics, chemistry, and courses that align themselves to those disciplines. So if you're in high school and it's your intention to embark on being engineers, the first thing that you should do is get up to date, get involved in doing these technical areas. Don't tell me that, oh, I do not like algebra, but yet I want to be an engineer. It's not making sense. I do not like geometry, but yet I want to be an engineer. I don't like physics, but yet I want to be an engineer. I do not like chemistry, but yet I want to be an engineer. That won't work. Those are the fundamentals for engineering. Show me one engineer, when I say engineer, not somebody that's called an engineer. So show me one engineer that's not mathematically capable. No, not one. Because everything that you do is based on math. The basic math for engineering is calculus. So how are you gonna do any kind of work, any kind of design, any kind of implementation? Well, you know, somebody could do implementation by just following a MOP, method of procedure. But are you an engineer? No, you're not. You know, for a better word of description, in my company, we would call these people technologists. They're auxiliaries to engineers, so they can do some duties that have some engineering concepts, but from inception they're not involved. They take what's already engineered and move that into production. So guys, if you're thinking about engineering, think about math. If you're thinking about engineering, think about physics. If you're thinking about engineering, think about chemistry. But don't listen to talks when people walk in and say, "Oh, what do you do? I'm an engineer." Where did you study? Where did you get this? Where did you go for the training to be an engineer? Oh, I didn't get any formal training. So how did you get yourself up to speed in the series of calculus? No, I don't know calculus. So how can you be an engineer? Tell me what system, one design. I'm not talking about using other people's design now. But tell me one design that's not involved with some math, some calculus. I'm gonna talk a bit about I'm an electrical engineer, so I can talk a bit on that. But other things, mechanically, I can also speak because the physics, had taught me quite a bit on systems. So let me touch on mechanical for a bit. If you're going to do systems, we have to work with feedback. So there's a lot of feedback involved in mechanical systems. Feedback means that a portion of the output is going to be fed back into the input. That involves differential equations. So when it's fed back to the input, we're gonna take a difference in what you're feeding, the initial feed, added to what is fed back, or take a difference and feed back in the system. I'm not going to go in very much details, but math has to be applied. Math has to be applied so as to avoid what's called positive feedback that can create oscillation. What that means, if what's fed into the system is added to what's returned to the system, then the input will be greater and greater at each time that the delta is fed back into the system, or the delta is a portion of the output is fed back into the system. So we're in for problems. Now, I'm going to touch a bit on, basic electricity that we all know about, or transmission of electricity. We see light comes into our house, but it's more than just seeing a piece of wire running on a pole. There is generation, there is transmission, there is distribution. So we generate from the plant, whether it be a steam turbine, whatever generating plant we generate. Then we do transmission. Now, when we transmit at kilovolts, megavolts, high voltage levels. Of course, with the intention that you're going to get in your house 120, 220. But we're talking about 3,800 or 38,000 volts being transmitted, or more, 69 kV, 38 kV, whatever being transmitted. This has to be distance. This has limited distance limitation. Where am I going here? Distance limitation. A mat has to come in here as to where repeaters or amplifiers, let me say amplifiers, are placed so as to regenerate or get back that 69 kV or 138 kV, as a case may be. So we have, again, the mat. And if for those who may have done some college and some physics, you know that there is some proportionality that you have to. I think it's resistance and resistivity and length and cross-sectional area of the wire gauge. Those have to be taken in consideration as to where we put the repeaters or the amplifiers. Again, we also have radio transmission. We also have repeaters. These are not placed at will, because we have transmission medium. Things go through this medium, experience what's called degradation. So the signal will be degraded. It has to be recovered, then retransmitted to get to distant location. So again, we're talking about math and physics in play. If you're going to go in some finer details, there's also the chemistry that gets involved, because you're talking about elements and matter and current flow and all kinds of different things that surround the atoms and molecules and compounds. These all work themselves into engineering concepts and otherwise. So again, for the youths who have interest, or for the young people who have interest in becoming engineer, please don't listen too much of the talk about who is an engineer, but listen to real engineers. Ensure that the concept is not just a repetition for doing math, but get the concept, understand what it means when you're doing problems. Because if you understand what that means, what you learn in a regular math class is preparation for future math studies. I always, being a tutor, being an instructor, I'm always saying to some of my students, or most of my students, it's not all, that I do not want them to recite any equation, because many use it, do a recitation, but not understanding what's actually happening. One that frequently comes to my mind, or I go over frequently, is what's called, for those who have some exposure to math, the quadratic equation. And I see so many people come by for tutoring, but yet they're telling me I don't remember the formula for the quadratic equation. Did you understand it in the first place? Once you understand, you will never lose it. So don't use repetition. Of course, there are things that you may have to commit to memory, but math is logic. Math can be proven. So embark in proving everything. Work in proving everything. That will give you greater insight. That will give you greater understanding. So, back to the quadratic equation a bit. I was talking to this young man a few days ago about the quadratic equation. So his question was, how is that going to help me in school? How is that going to be applied? So that's where concepts come into play. So I had to go through the motion of explaining to him that math is a model. So the quadratic equation, one could model that this can be used on is a tossing of a ball. So we can have an equation that models the tossing of, say, a ball, a cricket ball, a football. I'm not too much of a sports person, but any ball that you just tossing something, it's gonna follow that trajectory. It's gonna follow a certain path, and that can be modeled by a quadratic equation. Now, how is that gonna help us? We can use the solutions to that quadratic equation to make determination as to how high that ball can go, what time it returns to the floor, to the earth, and we can look at different steps as that ball travels along the way. So, and that's really simplifying everything. That's very simplified example. But math in itself models just about everything. But for example, again, with that regular equation, say we have like a regular equation and we want to find, what must I say now? The slope. We can model a slope or model a line and determine the slope of the line. That, again, can tell me a lot about an incline. What is this incline? Can it be traveled up? There has to be, we can't go above a certain slope and allow anything to travel along that slope, because with traction and gravity and everything, we're gonna roll back or tumble if the slope is not designed for anything to roll up and down. So that in itself is another example. But we can determine the slope. We can create models for even what we would call that instantaneous slope, because there are times when the slopes are not constant. When slopes are not constant, when I say constant, the slope is the same. It's like a straight line will have a constant slope. So again, if it's not a straight line, if the model is almost like parabolic, something resembling a horseshoe shape, then the slope is going to change. at each point. So we're gonna have instantaneous slope. So that's where you would say calculus or differentiation calculus would come into play. You know, we get the slope at different instances. And all those are fundamental to engineering concepts. I would love to, you know, go deeper into this, but because I'm driving, this is my drive time every morning that I'm going to work or coming from work, I set my phone on and just speak until I get home or get to work. But I hope that I may be able to perfect, you know, this concentration while I'm driving, so as to get a more streamlined, you know, so as to develop a more streamlined method of delivery. I want to be able to be a part of the educational travel for the youths. I think it's on me, it's impinged on me, it's one of my responsibilities to make sure that the real deal, the truth goes out there when it comes to education, especially in the technical field. You know, we have to, as educators, we have to give this, you know, some kind of, what must I say? We have to give this a bit of thought. Make sure, you know, we want to excite the interest of the young people, because if we don't, they're going to eventually fall apart. We need, how can we, you know, give insights? We have to know, we have to have some fundamentals, we have to have the basic foundation. But if you're going to say you are when you're not, you know, it's, you know, that's going to be a problem. So there has to be some kind of skills here to say who delivers what, and who are you when you're doing the delivery, and are you what you propose to be? Because that's also a very integral part of trying to excite the interest of a younger generation. We have to be true to it. We have to at least give great insight into what's needed. The prerequisite, of course, I'm always embarking on prerequisites, because without that, there is just no moving ahead. So that in itself, we have to ensure that it's understood. In everything, we need foundation. And if I'm gonna build a house and the foundation is not solid, or there is no foundation, then it's gonna crumble. Everything follows that method. So foundation, fundamentals should be looked into. We also need to understand that, you know, our choosing a vocation is more a part of the way we were socialized, how much we information, how must I say now, how organized, how equipped we are in that field. It's not saying that I want to be a doctor just because it floats, or I want to be a dentist because it sounds good, or I want to be a teacher because I like to be in front of a classroom, or I want to be an engineer because I'm interested in design, in making things. Yes, it's good to say I want to be all of these, but ensure that you're equipped with the right tools. And what the right tools being, you're educationally equipped. Okay? We all have abilities, but potential alone won't make it. You may have the potential to do anything. Most of us have potential, but is that enough? If we don't act on our potential, then it's useless. You know, I'll leave you with this example. If I have a ball or a bowler that's hanging above my house, it has the potential to destroy. But unless let go, it can sit there forever with the same potential to be destructive, because the force, you know, a little math again, I'm a math person, multiplied by the weight, or the force is the mass, you know, which is outside